Hello everyone, my name is Nidhi Singh and I'm assistant professor in SGVU-Pharmacy, that is a part of the solution. And today we are going to discuss the cycloalkanes. And in this cycloalkanes, this comes in the pharmaceutical chemistry in third semester. And let's start the topic. In this, we are going to study about the Sachi-Moore theory. So, what is Sachi-Moore theory? And also, we are going to study about the streams. Here, the student outcome is that they are going to know about Sachi-Moore theory and its limitations. That what is the Sachi-Moore theory and what are the limitations? And also, we are going to know about the streams and how many type of streams are there and what is strain and how many types of how many types of strain is there. And in the last lecture, we have already discussed about the two theories, that is your polymorphism theory, and the first one is your Bayer theory. And in the Bayer theory, it was that the ideal angle is that. Uh, the ideal angle is the alkane angle, that is 109.5 degree, and uh, and the angles that are shown by the cycloalkanes, if there is any strain, if that is less than that angle, then ideal angle, then they are the strain angle. So that is the Bayer angle theory, angle that is less than that. So in the cycloalkane and the cyclobutane, we are having the strain. So let's start this topic. Sachi-Moore theory. That is also known as the theory of stainless string. So here we have suggested that both large and small polymethylene rings should be strained, but Harman Sachi pointed out that larger rings needs to be strained because the carbon need not to be coplanar. So here the Bayer suggested in his theory, Bayer suggested that both large and the small polymethylene rings should be strained, and means here that where in this theory suggested that in larger and the smaller polymethylene rings they should be strained. But Herman Schwarzschild, that is another scientist, that also pointed out that the larger rings that the larger rings needs not to be strained because the carbon need not to be coplanar. Means the larger ring should not be strained because they are not in a coplanar situation. The Sachi theory proposed that higher member ring can become free from strain if all ring carbons are not forced into one plane. So he suggested that the higher member ring means more, which are having the higher carbon atom, they can become free from strain, which means they can become free from the strain if the ring carbons are not forced within one plane. Means if they are not forced to be coplanar or in one plane, then they are free from this strain that exhibit on the ring. So they exhibit in two non-planar puckered conformation, both of which are completely free from strain. These are called the chain form and the boat form. So these high ring members or the high member ring or the larger ring, they can become free from strain. They can become free from strain if all the ring carbons are not forced into one plane. They exhibit in two planar. Means here these higher member ring, they are existing in two planar, two non-planar pucker situation, means Winkle situation, Winkle conformation, and both both of which are completely free from strain, and both of the situation that both of the non-planar puckered conformation, these are free from the strain, and these are called the chair form and the boat form. So the both non-planar perfect conformations are called chain form and the board forms that are free from this stream. So here you can see that the chair interconversion of ring flip in cyclohexane. So cyclohexane is a higher member ring. Okay, cyclohexane. So there is a interconversion or a ring flip unit. You can see here. So here you can see this is the ring flip. This is your cyclohexane. This these are showing the carbon atom. These are showing the hydrogen atoms. These are the carbon atoms. This 1, 2, 3, 4, 5, and 6. So 6 is having the cyclohexane. This is interconversion and chair form. So this is the chair and this is the half chair. And this is the twist board form. And this is the board form. So this is the pucker up and right. This is the pucker up and right. And this is same as above. This is a situation which is written like this also. This is shown like this form also. And it is in the conversion into this form. So twist board composite sense. This is the half chair and this is the opposite sense chair. So this is the mechanism of your interconversion. Means your chair is converted into your interconverted into your half chair. It can be interconverted into a twist board. It can be it can be converted into your board form. So this is the pucker up and right. Next is your twist board opposite sense. So in this case, this is interconverted into your So in the Sachin theory, the theory of strainless string means here strain. The ring is not having any strain. So this theory is depend on that. Means the ring is not having any strain, that is strainless. This is that theory. This is Sachin theory. So in this, they suggested that both large and small polymethylene rings, both large and small should be strained. Means in case of bear that the either it is large ring or it is a small ring. Both rings should be strained. And means there is a strain on the ring. But that Hermann Sachi scientist soon pointed out that the larger rings need not to be strained. Means they need the larger small rings may be strained, but the larger ring should not be strained, need not to be strained because the carbon need not to be in coplanar. In case of Bayer's theory, the carbon is in the coplanar, but in case of this Hammond-Sachi theory, he pointed out that the larger rings should not be, need not to be in this need not to be in a strain situation, and the carbon need not to be in a coplanar situation. That is why he proposed a theory. In this theory, he proposed that the higher member ring, the members which are of higher ring, they can become free from strain. They can become free from strain if all the ring carbons are not forced into one plane. These Sachimo theory proposed that higher member ring can become free from strain. They can become free from strain when the ring carbons are not in a planar situation. That means if they are not in the same plane, then they can become free from that strain. And they exhibit into non-planar pocket conformation, or you can say the pocket conformation or winged conformation. So these higher rings, they can exhibit in two non-planar, means um, two non-planar winged conformation, and both of which are completely free from strain. And these higher member, which are showing the two non-planar pocket conformation, they can become free from these strains, and these coplanar pocket conformations are called the chain form and the board form. So in this chair interconversions, ring flips in cyclohexane. In this, you can see in the picture that this there is an interconversion in this cyclohexane. So this is the shear form, and secondly is all the shear form. There is a flipping in the ring, so they can exist in this form also. So here, secondly, this half shear can be interconverted into a half shear. Then it can be interconverted into a boat form also. So this is the pucker up and right, and this twist both opposite sense, it can be interconverted into your half chair and interconverted into your opposite sense chair. Next, the chair conformation is the most stable conformation of cyclohexane. And in chair cyclohexane, there are two types of position, axial and the equatorial. The axial positions point perpendicular to the plane of the ring, whereas the equatorial positions are around the plane of the ring. So, in the chair conformation, which is the most stable conformation of cyclohexane, the chair conformation, which is the most stable conformation of cyclohexane. In this, the chair form is the most stable conformation as compared to the board form. And in the chair cyclohexane, in the chair conformation, which is the most stable conformation, they exist in two positions. First is the axial, and second is the equatorial. So here in the figure, you can see the axial position, and secondly the equatorial position. So the axial position point perpendicular to the plane of the ring. These axial positions, these are the perpendicular, they show the perpendicular to the plane of the ring, whereas the equatorial position are around the plane of the ring. So these both these are showing the conformations of this cyclohexane. So this is the axial position which is perpendicular to the plane of the ring, and this equatorial is around the plane of the ring. Equatorial position are around the plane of the ring. So this is the axial and the equatorial position. Mix up of this axial and the equatorial position, and typical drawing showing all the axial and equatorial position. Each C looks tetrahedral, means if the carbons are having this tetrahedral angle, then they are not possessing any strain on them. So this in this chair and the equatorial position diagram that is showing the chain and the equatorial position, in this you can see that they are not they in this the carbon is looking tetrahedral, means there is no strain on the on this cyclohexane, which is a higher membrane, which is a higher member of this series. So once again, I'm telling you this in the Sachin theory that that the Bayer in his previous theory suggested that the larger and the smaller both of this type of rings, they are having the strain in them. But in the site, but the Harman Sache pointed out that the larger rings, they need not to be strained. They need they do not uh, they do not need they do not to be strained, or because the carbon should not be in the coplanar, need not to be in the coplanar. So in the Sachin theory, he proposed that the higher member ring can become free from strain. Like the higher member rings, the larger rings, they can become free from the strain if the ring carbons are not if the ring carbons are not in a coplanar situation, or are not in a planar situation, force not to be in a one plane. So they exhibit two non-planar puppet conformations, and which are free from the strain, and these two non-planar puppet conformations is the chair and the board form. So here, Sachimore theory has given the two forms, that is the chair form and the board form for the higher member ring, or you can say the larger ring. So here the example is given of the cyclohexane. In the cyclohexane, you can see there is an interconversion in the chair form. So so the chair, the chair conformation, that is the most stable conformation of cyclohexane. This chair conformation is the most stable conformation of cyclohexane. So in this chair conformation, which is the most stable conformation, are of two type. That is your two type of position. It is showing the two type of position. First is your axial and the second is the equatorial. So in the axial position, it points perpendicular. This axial position is pointing perpendicular to the plane of the ring, whereas the equatorial position are around the plane of the ring. So this axial position, this is pointing perpendicular. This is showing the perpendicular to the ring, to the plane of the ring, whereas the equatorial position, these are showing the position that is around the plane of the ring. So the axial position, these diagrams are showing the axial position, equatorial position, and both it is taking axial as well as the equatorial position. And this typical diagram that is showing all the axial and the equatorial position, and in this you can see that the carbon is showing the tetra. Carbon looks like a tetrahedron. Next, Sachi-Moore concept of the stainless. In order to account for the stability of the cycloalkane beyond cyclopentane, Sachi-Moore pointed out that such ring can become absolutely free of strain if all the rings carbons are not forced into one plane as was supposed by Baer. Same here also that Sachi-Moore he has pointed out that Sachi-Moore has pointed out that the such rings, these high rings, these high methyl rings or high methyl cycloalkanes, these can become absolutely free from this strain if they are not forced in a one plane. So this that was supposed by the Baer. That theory they pointed out wrong. If the ring assumes a such 3D condition, the normal tetrahedral angle of 109 degree 28 retained, and as a result, the strain within the ring is relieved. So, if the high alkene ring, high cycloalkane ring are assuming a 3D structure. So if they are assuming a 3D structure, then that normal tetrahedral ring, that the normal tetrahedral angle of that 109 degree 28, they are retained, and they are retained in that 3D structure, and they are not forced to be in a one plane, and in this the strain within the ring is relieved. So thus a cyclohexane can exist. So here the cyclohexane can exist in two forms, that is your boat form and the chair form. So here in the boat form, carbon 1, 2, 3, 4, 5 lies in a same plane, and the carbon 3 and 4 above the plane. So this 3 and 6 is above the plane. In the chair form, the carbon 1, 2, 4, 5, 1, 2, 4, 5, these are lying in the same plane, and 3 and 6 are 3, 6 is above the plane and 3 is below the plane. So in the the Sachi-Moore theory, in order to account for the stability of cycloalkanes beyond cyclopentane, the Sachi and Moore pointed out in 1918 that such rings can become absolutely free of strain if all the ring carbons are not forced into one plane as was supposed by Baer. If the ring assumes a such 3D condition, the normal tetrahedral angles of 109 degree 28 are retained, and as a result, the strain within the ring is relieved. And thus, cyclohexane can exist in two non-planar stainless forms, namely the boat form and the chair form. In the boat form, the carbon 1, 2, 3, 4, and 5 lies in the same plane, and the carbon 3 and 6 above the plane. As you can see in the picture, that in the board frame, this 1, 2, 4, and 5 are in the same plane, and 3 and 6 are above the plane. And in the chair form, you can see that 1, 2, 4, 5 are in the same plane, but 6 and 6 is above the plane, and 3 is below the plane. So energy profile of the interconversion of cyclohexane conformation. So in the energy profile, the chair conformation, in this conformation, all bonds are in staggered form, make molecule most stable pocket conformation. So in the chair conformation, the chair form, in this conformation, all bonds, the bonds between these carbon-carbon, these are all in a staggered form, and they molecule, this staggered form make the molecule more stable pocket conformation. And in the twist bond or skew bond conformation, in this conformation exists in between chair and the board conformation, and than both more stable than both more stable than boat but less stable than chair conformation. So in this twist boat or your screw boat conformation, in this the conformation exists in both chair and the boat conformation. This screw or the twist boat. This conformation exists in both conformation, in the chair as well as in the boat conformation. And these are more stable. These conformations are more stable than your board form, and but less stable than chair conformation. These are more stable than the board form, but these are less stable than the chair conformation. Next is your half chair conformation. So in this half chair conformation, this is highly unstable. This is highly unstable and strained conformation of cyclohexane. So this half chair conformation, it is highly unstable and strained conformation of cyclohexane. So half chair conformation is highly unstable, and it is the most strained conformation of this cyclohexane. But the chair conformation is most stable conformation, and it is the most stable pocket conformation. And in this, all bonds are in staggered form. So, but this half chair conformation, it is unstable and it is strained conformation of a cyclohexane. Next is your boat conformation. So in the boat conformation, it is less stable conformation than chair form by 6.8 kilocalorie per mole, and it is due to flat pole interaction of hydrogen atom. So in the boat form is the less stable. Means it is less stable conformation, and then the chair, less stable conformation than chair form, and by 6.8 kilocalorie per mole, and it is due to flat pole interaction, and this is due to flat pole interaction of hydrogen bond. So here the flat pole interaction of hydrogen bond, this is less stable conformation than chair form by 6.8 kilocalorie per mole, and it is due to platform interaction of hydrogen atom. So this is the energy profile of the interconversion. If the interconversion is happening between the cyclohexane conformation, then this is the energy profile. First, chair conformation, which is in which all the bonds are shown in the staggered position, and which makes the molecule stable form, stable pocket conformation. And twist boat or the screw boat conformation, these are more stable. This conformation is between the chair and the boat form, and this is more stable than the boat and less stable than the chair conformation. Secondly, the half chair conformation. In the half chair conformation, this is highly unstable. So this half chair conformation, this is highly unstable, and in this this is a strained conformation of the cyclohexane. So this is highly unstable. So this is unstable. Then your this is the unstable. Then your chair twist and the boat form, and it is very strained conformation of cyclohexane. Next is your boat conformation. It is less stable. This conformation, this boat conformation, is less stable conformation, then you cheer by 6.8 kilocalorie per mole, which is due to the flag pole interaction. So here there is a flag pole interaction between the hydrogen atom of your hydrogen atom. So due to the flag pole interaction of hydrogen atom, this boat conformation is less stable than the chair form, and it is also less stable than this twist boat or the screw boat conformation. Next, you can see the energy profile of the interconversion of your cyclohexane conformation. So the chair, this half chair, the boat is showing, their peaks are shown by the half chair and the chair. So in this, the boat is having 6.8 kilocalorie, less stable than this chair form, and the chair is the more stable coupled situation, because in this all bonds are in staggered position of the boat form. So here you can see there is the half chair. The energy requirement is very high, 12.1 kilocalorie per mole. So here this half chair, but in case of your boat, it is 6.8 kilocalorie per mole, and this is the steering repulsion between the boat conformation. Means here that flagpole interaction between the flagpole interaction of your hydrogen atom. This is the boat conformation. In the boat, there is this is highly unstable. This is unstable than the chair form because of the 6.8 kilocalorie per mole, and plus it in this 6.8 kilocalorie per mole. This is due to the flagpole interaction of the hydrogen atoms. So here you can see that there is a flagpole interaction of the hydrogen. In case of this chair, there is no flagpole interaction of the hydrogen atom. So this is the energy profile of the interconversion of the cyclohexane conformation. Now, if we are rotating this carbon up and down and rotate this carbon down, so here you can see if we are rotating this carbon, so here the hydrogen that is in the axial up position, and this is hydrogen that is equatorial down position. So here, if we are converting this, then there is, you can see there is a ring inversion process, and in this you can see the equatorial up and the axial down position. So here you can see the rotate this carbon up, rotate this carbon down. So here the carbon conformation, ring inversion process, axial up, equatorial down. Equatorial up. In this you can see the equatorial up, and in this the axial down. If we are interrotating this, if we are rotating this carbon, then if that position will become up, and that position this carbon position will become down, and this carbon position will become up. So here you can see in this hydrogen. This hydrogen is axial up, and this hydrogen is equatorial down. And in this, if we are this rotated form of this chair, and there is this hydrogen becomes down. When it is rotated, this hydrogen becomes up. Now this equatorial down position becomes the equatorial up position, and this axial up position becomes the axial down position. This is the chain conformation ring inversion process. Next is the strain. So next is the strain. So strain means, what does the strain mean? The strain means deformation of bond length and bond angle from their ideal value under the influence of internal force. So the strain here means that the deformation means the deformation of the bond length and the bond angle from the ideal value. And in this case, the ideal value is 109°28. So here in this ideal value, is the deformation of this bond length and the bond angle, and which is due to that value is the ideal value under the influence of your internal force. So under the influence of your internal force means when they are deforming this bond length and the bond angle from the ideal value, when there is an internal force is applied, when there is a deformation of bond length and the bond angle from their ideal value. This gives rise to an instability within a structure with higher internal energy. So when there is a deformation of bond length and the bond angle, and this due to this internal force, then it gives rise that it and due to this internal force, there is a rise to an instability. So there is an instability within a structure and with higher internal energy, and there is a higher internal energy. Um, so strain is term used for the energy associated with the system due to its geometry. So strain is a term that we are using here, that is using here for the energy associated with the energy that is associated with a system due to its geometry. And then when this due to its geometry, and when a bond length or bond angle is distorted, potential energy is stored in the molecule. This potential energy that is stored in the molecule is referred to as the strain or the strain energy. So here, when a bond length or bond angle is distorted, when a bond angle is distorted, then the potential energy is stored in a molecule, then this potential energy is stored in the molecule, and this potential energy that is stored in the molecule is referred to as the strain or the strain energy. So here strain means due to this internal force, there is a deformation of bond angle and the bond length, and from the ideal values. The ideal value is here 109 degree 28, and due to this internal force or the deformation, there is a instability within the structure with high internal energy. So there is an instability within a structure, and the strain is a term that is used for the energy associated with the energy. Strain is a term that is used for the energy associated with the system due to its geometry. So here, the energy that is associated with the system due to its geometry is known as your strain. And when a bond length or a bond angle is distorted, then there is a deformation, you can say, or you can say there is a distortion in the bond length or the bond angle, then there is a potential energy that is stored. That is a potential energy that is stored in the molecule, and this potential energy, when this potential energy that is stored in the molecule is referred to as the that is known as your strain or the strain energy. So first is your type of strain. So these the type of this strain is your torsional strain or your eclipse strain, and secondly, angle strain, and the third is your steric strain or the van der Waals strain. So the first is your torsal strain or the eclipse strain. So in your torsal strain or your eclipse strain is an increase in potential energy of the molecule due to repulsion between electrons in bond that do not share an atom. So here this torsal or the torsional strain or eclipsing strain is the increase in there is an increase in the potential energy of a molecule due to repulsion between electrons in the bond that do not share an atom. So here there is a repulsion. There is a repulsion between the electrons in bond that do not share an atom. So the atoms which are bonded with the carbon atom, in that atom there is a repulsion, and due to this repulsion between the electron in the bond, there is an increase in the potential energy of the molecule, and this is known as your torsional strain. This is known as your torsional strain or your eclipsing strain. So, torsional strain or the eclipsing strain is the strain is the increase in potential energy of a molecule due to the repulsion between electrons in bond that do not share an atom that do not share an atom. So the the atoms that the atoms they and when a molecule and when a molecule is able to rotate around the sigma bond, there is bond to be different level of torsional strain that vary with the placement of the substituents related to each other. This leads to different conformation of molecules such as staggered or eclipsed with different energy level, which leads to different level of stability. So here, if we are rotating the molecule, if we are rotating a molecule around sigma bond, then this torsional strain is at a different level, and this vary with the placement. This vary with the placement of the substituent that is related to each other, and this leads to different conformation, and this leads to different conformation of molecules. And due to this different conformation of molecules, these are staggered or the eclipsed, and there is a different energy level, and there is a different energy level which leads to different level of stability. So that different energy level, which the different conformations, which are the different conformation of molecules, which are showing a different energy level, that shows the different level of stability. So this torsion strain of 1,2 dichloroethane. So dichloroethane means here that this chloro 1 and 2. This is the ethane because it is having the two carbon atoms. So this is the ethane 1, 2 because on the first position and the second position there is a two carbon atoms. So these are 1, 2 dichloroethane. So in the sawhorse projection, the sawhorse projection. So in this there is a torsion strain between this chlorine chlorine. If we are rotating this 180 degrees centigrade, then 180 degrees, then there is no torsional strain. You can see here. So in the Newman projection also, there is a torsional strain between this chlorine and this chlorine. And if we are rotating this at 180 degrees centigrade, then there is no torsional strain. You can see here. So here, as you can see here written that this leads to different conformations of molecules such as a staggered or eclipse at different energy level, which leads to the different level of stability. So here you can see this is now a stable molecule. This is a stable molecule. So again, I am repeating that this torsional strain or the eclipse strain, this is the increase in potential energy. This is the increase in the potential energy of a molecule due to the repulsion. Due to the repulsion between electrons, there is a repulsion between the electrons in the bond that do not share an atom. So here there is a repulsion. Here there is a repulsion between the electrons in bond. These are not sharing any atom. Which do not share any atom. So there this torsional strain or eclipsing strain is the increase. There is an increase in the potential energy. If the potential energy is increased due to this impulsion with electrons in bond that do not share an atom. Next, when a molecule is able to rotate, when a molecule is rotating. So here you can see in the Somers projection, in the Newman projection, this carbon-carbons are bonded with a single bond. So if they can be able to rotate. So these molecules, these 1,2 dichloroethane, these are able to rotate around a sigma bond, and there is a bond, to be different level of this torsional strain that vary with the placement of the substituent relative to each other, and this leads to this leads to the different conformation. This leads to the different conformation of molecules that is staggered or eclipsed, and there is a different energy level. and there is a different energy level, and this leads to different level of stability. So here there is a different level of stability here. You can see, and in the torsional strain or the eclipse in strain, it is the increase in the potential energy of a molecule, and there is a repulsion between the electron in the bond that do not share an atom, and this due to this rotating of around the sigma bond, this this leads to different conformations of molecule, that is a staggered or the eclipse, and there is a different energy level, and which leads to different level of stability. So where our stability, finally we need the stability, and then we got a stable molecule when we are rotating around a sigma bond. So here you can see this is the torsional strain of 1,2-dichloroethane. In the Sawhorse projection, this chlorine is forming a torsion strain, and when we are rotating this 180 degrees, then we are getting here a stable molecule. And again in the Newman projection also, this chlorine is having a torsion strain. So if we are rotating around them, then they are around rotating at 180 degrees, then there is a stable compound is formed. Next is your torsional strain in cyclopropane. So in case of torsional strain in cyclopropane, here you can see this is a cyclopropane structure, and it is same as this if you view like this from the eye. So in the Newman projection, note how hydrogens are eclipsed. So here you can see in the Newman projection, you can see here the hydrogens are eclipsed in a position. And here in the cis, you can see there is a severe torsional strain, and when it is rotating, then there is a mild torsional strain. There is a mild torsional strain because this is having a interaction. So there is a mild torsion strain. Second is your angle strain. So angle strain is the increase in potential energy of a molecule due to bond angle deviating from the ideal value, and this is the increase. There is an increase in the potential energy of a molecule due to the bond angle deviating from the ideal value. So here the bond angles are deviating from the ideal value. So the cyclic molecules are an excellent example to demonstrate this angle strain. An element that has a very large amount of angle strain is your cyclopropane. Cyclopropane is having a very large amount of angle strain. This theory is given by the Beers also. First, carbon and cyclopropane want to be in 109.5 degree angle with each other. However, due to the symmetry of the molecule, the carbon are forced into 60-degree angle with each other. This causes severe strain in the molecule. So as you can see, there is a this cyclopropane. In this, you can see a severe angle strain because this is having a 60 degree, and their ideal value is 109.5 degree. So this deviation, there is this much angle we needed, and that is why this cyclopropane is existing a very high, a very serious strain in this molecule. As you can see, all the carbons are sp3 hybridized, and the expected bond angle should be 109.5 degree. And in this cyclobutane, there is a deviation only 19.5, which is much lesser than this cyclopropane. And this exists as a puckered ring conformation. And in this case, cyclopentane, there is a deviation of 1.5 degree. So this exists as a open angular conformation. Next is the steric strain or the van der Waals strain. So in this, the steric strain can also be referred to as steric hindrance, which is related to van der Waals repulsion, or the strain that occurs as the distance between two atoms of substituents decreases. In the steric strain, you can also refer to as a steric hindrance, and this is related to your van der Waals repulsion, or the strain that occurs as the distance between two atoms or substituent decreases. And the steric strain occurs when multiple substituents are close together and cannot be separated by rotation. So in this steric strain or the van der Waals strain, this cannot be separated by rotation, and in this is also referred to as a steric hindrance. and in or it is also referred to as the van der Waals strain, van der Waals repulsion. And this occurs at the distance between two atoms or substituent decreases. So the distance between the two atoms or the two substituent when decreases, then the steric strain or the steric hindrance occurred there. So the steric strain occurs when multiple substituents are close together. So this steric strain occurs when multiple substituents are occurring there, are close there, and they cannot be separated by a rotation. So steric strain is the increase in potential energy of the molecule due to the repulsion between electrons in atoms that are not directly bound to each other. So these are not directly each other, and there is a having a steric strain, and this cannot be separated by the rotation also. Another question. What is the name of the compound and how many carbon atoms of the compound? So this is the name of the compound, which is cyclohexane. Sorry, this is your 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So cyclohexane, and it is having the 10 carbon atoms. What is the IUPAC name of the following compound? That is your B. 2-methyl bicyclo 2,2,1 haptene. What is the IUPAC name of the following compound? That is your 1-isopropyl 2,4 or dimethyl cyclohexane. This is the cyclohexane, and on the 2 and the 4 there are methyl is present, and the 1 position is isopropyl is present. Next, which of the following numeral projection does not represent 2-methyl hexane? That is your C, 3. Which among of the following compound explode on contact with oxygen? That is your cyclopropane. Which of the following cycloalkane has the least free space? That is your C, cyclohexane. These are the references from where you can study this topic. Cyclohexane. Thank you so much for today's lecture.